Hello, and welcome to Mr. Ambrose's AP Calculus BC video on series. Before I get started with some new material, I just want to review the topic that we ended up with in class yesterday, and that was P-series. Now, a P-series is going to be a series that has general term of 1 over n raised to the p power, where that power of p is a number greater than 0. Now, P-series, it'll be easy to determine whether they converge or diverge just by examining that power of p. Because if p is greater than 1, then we know that the P-series will converge. However, if p is between 0 and 1, where it could be inclusive at 1, then we can conclude that the P-series diverges. So let's actually look at an example with this P-series in action. So here we have an example to determine the convergence of the series with general term of 1 over the 5th root of n to the 6th power. Upon initial inspection, this particular series may not look like a P-series. However, if we rewrite the denominator as n to the 6th over 5 power, we see that this is definitely indeed in the form of our P-series. And in particular, the p-value of this P-series is equal to 6 over 5, which we know is greater than 1, so we can conclude that this particular P-series converges. And so you can see this is a very quick and easy way to determine the convergence of these P-series, and I did not have to perform the integral test. So in a way, your P-series is going to be very much like your geometric series, and you'll probably thank your lucky stars whenever you come across one of these P-series. So now I'd like to go over some other ad hoc rules that you're going to come across when you're trying to determine the convergence of a series. The first of these rules is that when we multiply a series by a non-zero constant, this will not affect the overall convergence of that particular series. So let's consider the series here with general term of 1 over n. If you recall, this is specifically our harmonic series. And we know that the harmonic series diverges. So if we were to take the general term of 1 over n and perhaps multiply it by the constant of pi, well, this resultant series is still going to diverge because we only multiplied the harmonic series by a constant of pi. And if you think about it, when a series diverges, that means, in this case at least, that the sum is infinite. And if you multiply infinity by a constant of pi, we still end up with infinity, which means our series diverges. If we consider this particular series here, hopefully once again you can recognize that this is going to be a P-series, and in particular our p-value is 2, which is greater than 1, so this particular P-series converges. Well, if we take the general term of 1 over n squared, and perhaps we multiply it now by the number e, well, this resultant series with general term of e over n squared is also going to converge, because we're just essentially multiplying this particular P-series here, which converges, by a constant. And remember, when a series converges, that means it has a sum. And so if you multiply a finite sum by another constant, we should still end up with another finite sum. The next ad hoc rule that you need to know when working with series is that if we eliminate a finite number of terms from a particular series, this will not affect the overall convergence of that series. The example I'd like to look at here, once again, has general term of 1 over n. Now, if you're not starting to recognize this particular general term, trust me, you will. This is the general term to our harmonic series, which we know that the harmonic series diverges. This series here, however, doesn't start off at n equals to 1, so this isn't exactly the harmonic series. Instead, the first term here is the billionth term of the harmonic series. So technically, this series we have here is the harmonic series less a finite number of terms. Now, I claim that while I'm taking away a billion terms from this particular harmonic series, I claim that that will not affect the fact that this series here will still diverge. Because while a billion terms is a lot of terms, if we add them all up, we'll get a finite number. And if we subtract a finite number from infinity, well, we still get infinity. So this particular series here will diverge, even though I'm taking away a billion terms away from this particular harmonic series. The last of the ad hoc rules that you need to be aware of when working with series is that if we know that two series converge, then the sum or difference of those series will also have to converge. The example that we have here, you'll notice that I'm adding up two different series. The first series with general term of 1 over n cubed, hopefully you're starting to recognize this series here, because this series here is our p series. In particular, the p-value here is 3, which we know is greater than 1, so this p series converges. The second series that we have here, with general term of 1/2 all raised to the nth power, here's where you thank your lucky stars, because this series is our geometric series. The r value of this geometric series is 1/2, and since 1/2 is definitely between -1 and 1, this series here, we know that this geometric series converges. So in this example, we have two series that both converge. And remember, when a series converges, that means that it has an actual sum. So if we add a finite sum to another finite sum, well, overall, we should end up with a finite number. And so, with the addition of these two series being a finite number, the sum of these two series should end up with an overall resultant convergent series. Now, if I change the addition sign to subtraction, hopefully that won't alter how you feel about this particular rule, because in this case, if anything, if we took the difference between these two finite numbers, if anything, this finite number here would most likely be less than if we had just added the two series together. So once again, the overall end result should be a convergent series. Well, at this point, I thank you guys for tuning in and listening to some math on your day off. I'm sure it wasn't easy, but thanks again, and I hope that you get to enjoy the rest of your day, and I will see you guys tomorrow. Take care.